Following on from some of our earlier videos, we got to this stage here where this part of the string plus this part of the string must equal the total length of the string. So we got to this stage here, but in order for us to really understand what this is talking about, we would create a scenario just so that we can get an idea of what's going on. We would make the length of our string to be 12, and then we would make A here to be 10 and B here to be 2. So when we plot this into a graph plotter, it would then give us this. So this is our A here, 10, 10, and this here is our B here, and then the length of our string must always be 12. So anything that lies on this red line here is satisfying our constraint here. Okay, so we got to this stage here. In order for us to understand what's going on, we would create a scenario here where we would insert 12, 10, and 2 into here, and then that would then give us this. Now, to find out where the ball will settle, we need to minimize y. We need to find a point where y would be at its lowest point, and so when we are here, we would then use implicit differentiation to take us to here. And it turns out that when you make this in such a way that this side equals this side, that's when y will be at its lowest point. So now if you get a graph plotter and plot this, get a graph plotter. Depending on the quality of your graph plotter, you should be able to plot this this graph here. So for our scenario, remember we are making this to be 10 and then B here to be 2. We don't care. We don't care about the length of a string, because when you use implicit differentiation, the L, the capital L, disappears. Okay, so if you get a graph plotter and plot this, hang on. So get a graph plotter and plot this, where you insert 10 into the A, and then B, insert the 2 into the B, and then if you plot this whole thing here, it will give you this blue line here. It will give you this blue line here. So what this is saying is that any point on this blue line, you will satisfy this condition here. Okay. Remember, we started out with this. We want to find out where y would be at its minimum. So we would use implicit differentiation to take us to this here. So any point on this blue line here will satisfy this condition. So for example, if you choose, let's say 5 here, comma 1 here, this here will be 5. This here will be 25. This here would be 1. So if you choose this point here, 5, 1 here. So looking at this here, it will be 5 over 25 down here plus 1. And then on this side here, remember we are putting 10 into here. So 10 take away, remember this here is 5. 10 take away 5. That will be 5 here. And then at the bottom here, 10 take away 5, that will be 5, and then it will be 25 here, and this here will also be 1 here. Same as over here. Basically, any point on this blue line, you will satisfy this thing here. Okay. So this point here, you will satisfy this, but you wouldn't really at this point here. You wouldn't satisfy this. Looking at this point here. Let's say looking at this point here, if you look at this point here, you would satisfy this, but you wouldn't satisfy this. Looking at this point here, let's say this point here, you would satisfy this, but you wouldn't satisfy this. But then, if you look at this point here, you would satisfy this, and you would also satisfy this, meaning that our ball will settle right here, because right here, the derivative will be 0, and also it satisfies our constraint here. Okay, around here it would satisfy. Around here it would satisfy this, but it wouldn't satisfy this. So we basically want to find a point where it would satisfy this, and it will satisfy the red line. Basically, it will settle right here. You could use algebra to really solve this, but it is really tedious, and we're going to leave that. We're just going to use a graph plotter and in order to answer the question. Okay, we're just going to use a graph plotter to answer our question.